Okay, so 5.8, sketching graphs of derivatives. So it says focus on the slope of f. Okay, because we know slope is the same as saying the derivative. Okay, the slope of f is the y value of f prime. Okay. Before we draw these sketches, I want to write some things in the margin. Okay, kind of refresher of, what it means to have f increasing, decreasing, etc. So if f is increasing, we know that the derivative is what? Greater than 0, positive. Okay. If f prime is increasing, we know that the second derivative is positive. And if the second derivative is positive, what is the concavity of f? Up. Concave up. Okay, so now we look at decreasing. So if f is decreasing, we know that's the same as saying that f prime is negative, less than 0. So if f prime is decreasing, this implies that f double prime is negative, also less than 0. And if the second derivative is less than 0, then what's the concavity of f? Down, right? Concave down. Okay, so just having that off to the side help us refer to it while we're drawing these graphs. So on the first one, they give us the graph of the function f of x, and they want us to sketch the derivative. So when we're looking at this, we need to look at the slope of each part of this function, because that's going to tell us how we can draw the derivative. So for example, we have this section of the function here. What slope would that be? Positive or negative? Positive. Okay. What about this next part here? Negative. And then the last part? Positive. Okay. What about at each of the peaks and valleys? 0. Okay, so right here and right here are going to be 0 at the first derivative because that represents the slope at that point. Okay. So another thing I want us to look at here is what type of function would this be? What type of parent function? Cubic, right? So if we were asked to graph the derivative, what would be the derivative of a cubic function? A quadratic. So notice that our cubic function went positive, negative, positive, which means it's a positive cubic function. So our derivative would be a positive quadratic function. Okay. So we know it's going to be a positive quadratic, and we know that where the f prime is equal to 0, so at that peak and valley, that is going to correspond on where those x-intercepts are going to be. Okay, so using that, I'm able to draw a sketch of what the derivative would look like. Okay, so this one's not too bad. When we go from function two functions derivative because we're following the same train of thought that we've been doing all year, talking about derivatives, right? The other one is where it can get confusing because on the next one, it gives us the derivative, but it wants us to sketch the graph of f. So it wants us to work backwards. And so what this is introducing to us is that concept of integration. Okay. So for this one, okay, first just looking at this, again, we can see that this is what type of parent function? A cubic, right? And if we want to get the original function, what did we have to take the derivative of to get a cubic? Or x to the fourth, right? Yeah, x to the fourth. Okay, so that means when we draw our original function, we're going to have a function that looks like x to the fourth, which has what type of shape? Looks like a W, right? Okay, so that's the end goal. We know it's going to look like some sort of W. So to figure out how this is going to go, we're still going to look at where it's positive or negative. But since we're looking at the derivative, remember everything below the x-axis is going to be negative, and everything above the x-axis is going to be positive. So I'm going to first label that part. So I have negative, negative, positive, positive. Okay, so what this is telling me is that when I draw my function is going to go down, right? Because the first part of this function is negative. So I know the first part is going to start going down. Okay. Okay. Then the next part, the part that I did green above the x-axis, is positive, so I know my function is going to start to go back up. Okay, the next part is negative, so I know it's going to go back down. Okay, and then the last part's positive, so I know it's going to go back up. Okay, this is our function of f. Okay. What's nice about this is that our derivative identified where our maximum and minimum values were going to be. And that is right here when f prime is equal to 0. These are our critical points. And so based on how I drew the graph of I think I wrote f prime. This is supposed to be just f right here. Okay, so when I drew this graph, I can identify based off of where my peaks and valleys are is where the maximum and minimums are. So this very first one right here is representing a what? A minimum, because right here we can see it on our previous graph. It's representing a minimum. We also know it's representing a minimum because it went from negative to positive. Okay, so this is representing our minimum, and we see that here on the graph. Okay, what is the second one representing? A maximum, because it went from positive to negative, and we see that up here. That's our maximum. Okay, and then I kind of made the graph a little lopsided here because technically this one right here is representing what? That last one? A minimum, so it's going to represent right here. Okay. And then one other thing that we know about this graph is it also identifies our points of inflection. Okay. And what's important about the points of inflection, so we know the points of inflection are going to be when the second derivative is equal to 0. Okay, Okay, so that's these points here on the original derivative graph. This is my point of inflection. What the point of inflection tells us about the original function is where it changes concavity. Okay, so it's saying that we're going to change concavity here and here, which we do. We go from concave up and then concave down. Okay, then we go from concave down to concave up. So these lines are representing our points of inflection on the original, the points of inflection on that derivative function that is telling us where we change concavity on the original function f. Okay. So the main part here is, okay, we drew the function, right? That's the main idea. All the other part is just correlating what we've learned so far. Any questions on these first two graphs? Okay, so I'm going to do the first one on the practice. And these first ones say, here are the graph. Okay, so it's giving us the graph of f, and it wants us to sketch the derivative. So this is going to be like the first one that we did. Okay, so the reason why I want to do this one with you guys is because we notice something happening here. And what's happening? A cusp, right? Which means what?
There's no derivative.
It's not differentiable at that point, right? We can't find f prime of x at that point because of that cusp, okay? So when we are taking the derivative of this function, it's going to end up looking like a piecewise function, okay? So knowing that, we can also see distinctly that this looks like almost two separate functions. We have this function right here, which looks what? Linear. And then this function right here looks like it's part of what? A quadratic. Okay, so if we're doing a piecewise function, taking the derivative, what type of function should derive from a linear function? A flat line, which is what type of function? Constant. And then from a quadratic? Linear. Okay, so that's what we're going to do. So looking at this first part here, we said this is linear. Is this a positive linear or a negative linear? Positive. And could someone tell me what that slope is?
2.
It's 2. So where am I going to draw my constant graph? At 2. Okay, so this is right here. Well, let me change colors. Okay, and then for the quadratic one, we're not able to say exactly what that slope is. We just know it's going to be linear. And since this part of the quadratic is going down, are we going to have a positive linear or a negative linear? Negative linear. So it's going to look something like this. Okay, we see that discontinuity there because of the cusps. It's not differentiable at that point. Yes?
Would the hole be below the x-axis?
That's a great point. Yeah, we could do that. We can move it down further. Just know that this is an approximation, right? Because we can't get what the exact derivative is going to be because we don't have more information, right? We just have this sketch here. Okay. Any questions on this one? Because of this section right here, do you see it almost looks like a sharp corner or a cusp? So we know it's not differentiable there. The next one I want to look at is number 4. Okay, so you'll notice on number 4, this one is the opposite. Now, this is like the second example we did. It gives us the derivative and it wants us to find the possible graph of f. So again, this is broken apart. It's piecewise. We see 2 distinctive functions here. We have this one, which is what? Quadratic. And if we're trying to find the original function, what would we have to take the derivative of to get a quadratic? A cubic. So we know this one is going to be a cubic. Okay. And then this one, what type of function is this one? Linear, right? And in order to take the derivative and get something linear, our original function had to be quadratic. So we're going to have a cubic and we're going to have a quadratic. Okay. The next thing that we can do, since this is the derivative, we know that we have critical points right here. Okay. And that is when f prime is equal to 0. We can also figure out if these are going to be maximum or minimum values by labeling if this is positive or negative. So this part is negative, this is positive, this is positive. Right? Because it's below the x-axis, above the x-axis. Okay? So that first one is going from positive to negative. So that's going to be a maximum. And then going from negative to positive, that's going to be a minimum. So when I draw this cubic, this tells me that I am going to have a maximum, then a minimum. So it's going to look like it goes up in a curve, then back down. I also know that I'm going to start going up because this part right here is positive. So since this is positive, I'm going to start going up. Then this negative part means I'm going to start going down. And this positive part tells me I'm going to go back up. So it's going to look like something like this. Okay, maybe I should not have it cross that line there, the axis I mean. Let me draw it a little nicer. There. Okay. Okay, on this derivative here, I also see what? What does this represent? A discon. Yes, question.
Does it matter like what y value is?
The only thing that matters is that, I mean, no, it doesn't really matter because we're drawing a sketch of what the original function is, which means there's so many different functions that we could have when we take the derivative because we could have constants that go away, right? So, no, not in this particular instance because it's just telling us to draw a sketch. Okay, so yes, you guys are correct here. We're going to have a discontinuity, which means when I'm drawing this function, what should I add to this part? A cusp. Okay, so before I draw that cusp, I know that you guys said, okay, this is linear, so I needed to have originally a quadratic. So looking at this linear, would this be representing a positive or negative? Negative, because it's below the x-axis, okay? Which means when I draw that quadratic portion, I need to draw the portion that's going down, right? Not the portion like the other one that's going up. So it's going to look something like that. Okay, so this is representing f of x, our original function.